Okay, today you have the talk of Professor Wen from the Technical University of Munich. It's a great pleasure for me to have Professor Wen here. I haven't met him the first time. It was in UK, in a UK Cancer Conference.
Long time ago.
2008, 2007. And since then we have been quite close friends. And it's the second time that he's here. And you have him for this talk. Just to mention, the position that's occupied by Professor Wen now is the same that was occupied by Professor Lucy some years ago. When I was visiting him, I had the chance to sit in the same sofa that was of Professor Musselt a long time ago. Just some few words about the speaker. Professor Wen is the chair professor and head of the Institute of Thermodynamics in the Technical University of Munich. Prior to his current position, he was the chair professor at the University of Leeds and Beihang University, and had he worked in various academic positions at the Queen Mary University of London. His research is focused on heat, namely how heat is produced, transported, stored, and utilized across different scales via nanomaterials, nanosurface, with target applications in energy and aerospace engineering. He has taken a multiscale approach, both experimentally and numerically, from nanoscale to bulk scale, to investigate fundamentals of flow, heat transfer, and reaction across scales, and apply these fundamentals cross-disciplinary into different sectors. Resuming, it is related to most of his knowledge is related to our work, and his talk will be really important for us here. Founded by UK, EU, China, German research councils, and many industrial partners, including two prestigious European Research Center grants. His research has produced over 20 patents, 400 journal publications, with total citation, he has more than 25,000 citations, and his age index is about 73. He is a member of the Academy of European and Institute of Nanotechnology. He is an editor-in-chief of Advancing Aerodynamics and an associate editor of Applied Thermoengineering. It's a great pleasure for us to have him here, and we are excited for your talk. For him.
Okay, thank you, Gerhard, for the nice introduction. And also, it's a very pleasure for me to come back to St. Carlos again. My first visit in Brazil is St. Carlos, which is 2010. Yeah. So Gerhard organized a small workshop that I had the fortunately to come to here. Since then, I visited Brazil many times to different cities, different places, and unfortunately, I can't speak any Portuguese. So, but I'm learning German. I'm now working in Technical University of German, Technical University of Munich. So I have to sort of studying language training again. Unfortunately, no Portuguese. So as mentioned, Gerhard mentioned, I work a lot of things relating to heat from multi-scale approach. So today I also have the opportunity to visit the labs of Professor Libaski. And I'm very impressed about his multi-phase and two-phase flow research, flow volumes from different scales. So that's why I'm thinking maybe I'm talking about something also similar in this similar area. We're talking about fundamental part of phase change from different scales. I'm going to start with a very brief introduction. TUM, which is, I don't know whether you can see the point. I put a point here, so we are somehow here. So it takes us more than 11 hours in flight. We arrived yesterday, midnight. So it's a long distance, but this one is in the very southern part of Germany, very close to Alps. Over the Alps, you reach Italy. So the university is very famous. It's also one of the best in Germany. It's always ranked number one, or sometimes very rare cases is number 2. So normally it's number 1, and the world ranking is always in top 30. It's also a massive university, has nearly 60,000 students, but there's only have 600 professors also. So if you calculate the professor-student ratios is very, very low. That's why we have a very big classes. We've been used to give classes, 400 students. So it's only have 8 departments or schools, 600 professors. It's have 18 Nobel Prize winners. It was built in 1868. Now let's talk about something we are familiar, phase change. So phase change actually is slightly different. There's another definition called phase transition. If you talk about the people in physics, they talk about different alpha phase to gamma phase. That's called a secondary phase transition. But phase change we define as more sort of first stage for phase transition involve latent heat. That's where we have melting and boiling, evaporation, everything related. This is a multi-phase, is a phase change. So phase change actually has a wide range of applications, for water applications, for power applications, also for thermal regulation, different aspects, different applications. So very, very much interested in understanding the heat transfer process during the phase change. If you look about heat flux, so this is talking about different levels and then temperature different levels. So phase change and also heat transfer is very much important to relate what happening, relating heat flux and temperature together. So phase change is very fundamental. It's also very common. But how much do we understand about phase change is different questions. So if we see the starting point of phase change, people always refer this to the classical nucleation theory, because when phase changing starts, it coming generating something that are existing from liquid to vapor. So what's the initial phase that is starting? So this process called nucleation. Nucleation normally depends on the nucleation theory. For example, this is classical because it's more than 100 years old. That's why it's so classical. So people have to define critical nucleoside. So this is no matter a gelatin bubble or gelatin condensation or gelatin icing, you always have an initial nucleation site. So this is depending on the competition of the free energy. When you're forming a phase, you create a new energy and you destroy some energy in the past. So you need to make the balance. The energy makes it flows in the way of second law of thermodynamics. So that defines the point of this point. So if the nucleation size is larger, then this critical nucleation size, this phase change is just unstoppable. It's just starting. If the nucleation size is smaller than this, then phase change is never going to happen. So this origin, this is a starting point of the nucleation. But do you understand nucleation? So is it classical? It's been developed for more than 100 years. It has a lot of limitations. For example, you can't describe the phase changing at a small scale, and which is a lot smaller than a couple hundred nanometers. You can't describe the clustering of molecules during this pre-phase, these pre-nucleation clusters. The nucleation routes may not be one path, it maybe have a million paths. You have 2-stage nucleation, 3-stage nucleation. So a lot of things, this classical nucleation actually does not work, especially considering something goes to very small scale, something goes to very non-conventional fluid side. So this is our first question. So a lot of people here working in nucleation side, in chemistry people work, in physics people, materials people, because this is the original place for the control the materials quality in many cases. So second example, just talk about evaporation. So how water is evaporated looks pretty simple. People work on different concepts of evaporation, so they try to intensify this process. They can put something very radiative, very thermal absorptive at the bottom, or put some particles in the liquids, or put something floating on the top. They always want to try to concentrate the solar energy to produce and maximize the solar evaporation process. So clearly this sort of process, interfacial evaporator, it has a very high efficiency because most solar energy reach on the surface, that surface has the highest temperature, so it's helping to evaporate it quickly. So there are a lot of work on the solar evaporator. So if you look at this diagram. So there's a lot of high-profile papers. The papers published in Nature, published in Science in Pillars. They work on evaporation, especially evaporation on the surface. This surface is made up of hydrogeles with a lot of nanoporous materials. The strange things happens. This is theoretical limit. If you convert all the energy by latent heat to vapor, this is 1.47 is what you can get under one sun conditions. People reported all the much higher evaporation rate. So why they have such a evaporation rate? Then there's kind of a lot of assumptions. People talking about the possibilities of latent heat being reduced. But from thermodynamics, we know latent heat is a property. If you water is the latent heat you can find from property tables. They say the nanostructures, latent heat is largely reduced. Okay, this is one popular assumptions trying to explain why there's so much higher evaporation rate. The other peoples like MIT, a group of MIT, they propose this is kind of photomolecular effects. We know there's a photoelectron effects. That's one of the Nobel Prize winning back into 100 years ago. Photons can exciting electrons have these photon-electron effects. They propose something called photomolecular effects. Some of the photons they shoot on the surface. A class of the molecules they can be the links between different clusters can be cut off by these photons. So these are photomolecular effects. So they're trying to explain this, what happens, and why a simple evaporation case makes something so much difficult. I'll give you another example here, which is in the nanomedicine side, people using laser, especially high pulsed, high frequency lasers to do different medical treatment. They can do medical treatment, like an eye operation, for example. They can also do this by using different nanomaterials for controlled delivery, for controlled drug delivery and controlled therapies. And this is a paper also in Nature Nanotechnology. They talk about people using laser for the eye treatment, where they induce the nanobubbles. So the laser actually interacting with the materials produce nanobubbles. So these small bubbles that actually destroy, they kill the magnetic cells. So that's one of the things people work on. But if you look about the threshold, for example, at which how much power, how much laser affluence you need to input to produce these nanobubbles. So there's even given the same materials or the same nanoparticle diameters, the required, the reported laser power is order of magnitude different. So you remember this is a logarithm sort of scale. So there's a couple thousand different tons, different intense heat and power you need to put to generating different nano bubbles. So there's a lot of misunderstandings why these things happens. Then, if you look about the interactions of laser with these materials, it's actually much more complicated. So it involves the interactions of, for example, the photons, which is by the laser, with electrons. Then electron is equilibrated, then pass energy to photons. So there's a strong coupling for different matters between electrons and the photons and the photons. So there's a cascading of energy decay from photon energy to electron energy then to the photons. Then from the photons is passing energy to the surroundings, which can be either by conduction or either by induced bubbles. If we have very fast conditions, these bubble growth will be very, very fast. They can introduce different shock waves. Many people argue that this sort of shock wave is the underneath mechanisms to introduce cell damage. So these are a few examples I hope I'm giving to you shows how much complicated and different of this phase-changing behavior. This nanobubble is not only for this nanomedicine side, it also has been used for mainly for nanomaterials production. This is a metal. The interaction with a laser interaction with metals to produce bubbles and produce different nanoparticles. So this can be also used for process monitoring by using laser to excite some of the components for different plasmas, so that in a way of detecting Plasmodic nanobubbles is also can be controlled and produced by different lasers used for diagnosis and for controlled drug delivery. So there are many applications at this sort of nanoscale. Now let's have a look at phase change. We'll come back to the picture. Phase change is the first order phase transition involve latent heat. It's a very simple definition. We are very familiar with this, but if you look about inside, the origin of the nucleation, the starting point, we don't know. Classical nucleation normally doesn't work in these cases, especially at the very beginning. Phase change in extreme conditions, when it goes to very small, goes to nanoscale, there's a lot of mysterious understandings. When it goes to extreme fast, introduces shock waves, so all this becomes very much difficult. It's also when the interaction with different field, especially electromagnetic field, when the interaction with solar, so people call this a solar evaporation, in differentiating to thermal evaporation. Because the thermal evaporation probably is more standard, but the solar evaporation involves the light interaction with the electrons there. They may have some strange effects here. So how this materials interaction with the surface and on a different electromagnetic field is still very much unclear. Now this comes to what we are interested to do. We're trying to form a holistic approach, trying to understand the phase change in a lifetime spell. How phase change was starting? It's like a man, for example, how he was born. So during the pregnancy stage. So that's the nucleation stage. Okay, we want to understand pregnancy, and then we want to understand how this first bubble was produced, how first phase change was produced. So this is the born process. The baby was born, then starting growing, starting dying. Also, how this baby is interacting with the surroundings. What's the effect of this bubble coming to the surroundings? Introduce the thermal effects or mechanical effects. So that's why we are very much interested in understanding this whole holistic approach of phase change. That involves many sort of multi-scale nature. If you look about that scale, from nucleation, people talk about a class of tens of hundreds of molecules, which is normally below a couple of nanometers. So if you're starting from here all the way to the effects. From time scale, it's also nanosecond or below. Nucleation involves interactions of different molecules forming different metastable stages. That's very fast stage. So how we understand this and also apply this knowledge to our understandings of relating different applications, either for solar applications or for 3D metal plating process of nanomedicines. So that's the whole scenario we're hoping to cover, also interested to investigate. So we have been working on phase change from different aspects. So they are not always focused on one problem. Focus on one problem is always difficult. Also, it's very difficult if you focus on one problem, that you can get sustained funding support. So we have to open to different aspects. So we summarize the works we have been done. One is in the macroscopic, when we talk about boiling and evaporation mostly. So I will quickly go through this a few macroscopic experiments. So this is the first one. This is actually my PhD. I worked for 3 years when I was in University of Oxford, trying to understand how bubble was produced in a single channel, which is a 1 millimeter by 2 millimeter rectangular channels. So that's very similar to a lot of PhD students who are working here. Yeah, we're trying to see flow boiling. Okay, so we identified the confined bubbles. So how at that time, which was at the beginning of 2000, so people actually worries about it. They don't know too much about the flow boiling in micro nano channels, because this bubbles kind of goes, they induce a lot of fluctuations. So we measure all these, for example, this is pressure fluctuations. When bubble was confined with really big bubbles, it induce big pressures. So these pressures actually, they induce a lot of flow distributions. They also affect in saturation temperature locally. So this saturation temperature also changes and affect clearly the heat transfer coefficient will be changed accordingly. So this is somehow was a very early work. We integrating the measurement of pressure signals, local pressure signals, local temperature signals together with the visualizations together to see how this one single bubble can induce a global effects during the confined flow boiling stage. So I did a lot of experiments at that time, which is very, very interesting. So flow boiling, the second one, this actually is the ones still my predecessor has been worked on, Professor Satama in TUM, and they set up this alliance research rigs trying to understand the flow boilings of different organic fluids, especially for this sort of immersive cooling perspective. A lot of fluids has been used trying to put the electrolyte devices into the fluids, but they are limited by the critical heat flux. They try to understand what's the best, what's the highest heat transfer rate that paint goes up to. So we set up this one, and then we have developed a suite of techniques using PIVs for the flow visualization, shuttle graphs, and to understand the density destructions for the local temperature measurement, together with the high-speed cameras and the surfaces, so that we are able to forming a picture at the critical heat flux for these organic fluids, what's going to happen. That's a flow boiling second phase. Pool boiling side, we are very much concerned on the critical heat flux. So this is also one example we see. Because the heat flux, critical heat flux, when it happens, is because of instability. That's the classical Joule theory. You got gas, vapor is coming, liquid is coming, vapor is coming up, liquid is coming down, then you have instability at the surface. Why this instability can there? Because they have the different flow ways. Liquid come this way, gas coming that way. So they actually block the way, they block the path. So we propose something called artery channel design, so to allow efficient separation of fluid phase and the vapor phase. For example, so this is a porous media, the fluid is just coming from the top, but inside the porous media there are these channels. Those channels actually allow vapor to go. So this is actually separating the path. Fluids path is still coming from top, always keep wet in the surface. The bubble is produced, but produced bubble is going from the other way. So by this sort of methods, we can significantly increase the critical heat flux from about 1 megawatts to about 8 megawatts per square meters. Similar concept, this is a vapor chamber. This is a device based on phase change. This vapor chamber actually, this is a conventional one. You have evaporation here, you got condensation here. So all these different fender structures is trying to dissipate the heat. So this is the condensation part. Those fan structures are used for promoting the condensation process. So this is conventional. We use the basic concept of previous the designs. So we change the top part instead of those bilateral convection cooling on the condensers. So this is a condenser now. This condenser actually has a phase change happens here. So the vapor evaporated, it goes up, then they're condensed, coming down. They're condensed by the porous media, by the gravity effects together. So we efficiently change the condenser into a phase changing mode. So inside the conventional condenser, which is only a lateral convection happens, we got the evaporation and the cooling happens on the condensing side. So this is a new design, so it can give us a very, very good heat transfer performance. We are also developing a new sort of vapor chamber. Again, this is for electronic cooling, we call wicks. So instead of using different wicks for the liquid circulation, here now is really based on different patterns. By using different hydrophenicities and in the evaporator, for example, this is our evaporator. So everything is something like very hydrophilic. They absorb waters from different parts, like a spider web, they absorb waters. In the condenser, everything is hydrophobic. They form in different droplets. These droplets then accumulate together, they're forming this bridge. Once they form in this bridge, so the liquid is actually transported from the condenser to the evaporator quickly. So by this way, get rid of the limitations of the pores, then just using this manipulation of the surface property to induce the liquid circulation process. Another work is about loop heat pipe. This again is a piece of device. It's a phase change, evaporation in one place, using capillary forces to circulate the fluids inside, and the condensation is on the other side. So this is a piece of device widely used for the thermal control in aerospace. Because in aerospace, when you want to cooling everything, you have to use something very efficient. Also, always making sure that it works. So we developed somehow a new design of these two condensers, and also investigate this loop heat pipe under different accelerations. It may be accelerating or deaccelerating, so they are significantly affecting the fluid's redistributions inside. So those some of the works that has been widely used in thermal control for aerospace engineering. There's another phase changing in relation to very lower vapor pressure, lower pressure. When it goes to the lower pressure, here is below 2 kilopascal. The evaporation, the boiling things happens instantly if it's 20 degrees, because the boiling saturation temperature 2K is extremely lower, about 10 degrees or so. So how heat transfer happens at this lower temperature, at this lower pressure side. So we actually found out something very interesting, and especially a very unique, this is pancake jumping phenomenon when droplets starting evaporating. This evaporation force is too strong. They sort of generating a very big uplifting effect, and to push the droplets jumping out. So the contact time between the droplet and the surface can be significantly decreased. Now let's moving down to a bit small scale and trying to understand the different phases, flow boiling, evaporations, and also loop heat pipes. The fundamental part is visual evaporation. If we see a boiling process, we still confined, for example, this is a boiling, we're trying to understand what happens in the micro layer. This is the fundamental part. But if you want to go into this micro layer, there are some hypotheses we can probably understand by using some techniques, the thickness change, for example. We can use one or two thermocouples by measuring temperature change. But the whole picture actually is very much unclear. Mostly, and in the past we do flow boiling or boiling experiments, we're just using cameras to visualize the bubble dynamics. Moving down into this small scale, within this, also this very close to surface scale is always challenging. So if we look at the different techniques, techniques for the liquid temperature measurement, you can use thermocouples, and which again is limited by the size. The smallest the thermocouple size probably can go to 20 micrometers. It's also been limited by the you can use laser-induced fluorescence. Some of the people, especially biomedical people, they're using this with temperature-sensitive dyes. You observe the dye temperature, the dye's color change to indicate what's the temperature within a small layer. Total internal reflection fluorescence microscope type can also goes into limitations to about 100, 200 nanometers, because the evanescence waves can only reach on that region. That the temperature signal gave you a fluorescence signal that we can capture the temperature within small space scale. So this is on the temperature side. On the real world phase identification, because they're very closely, you can't clear differentiate what's the vapor, what's the liquid. So there are a lot of ways, optical ways, high-speed images, and PI ways, and the lasers, especially the reflections has been used to identify different phases. Solid temperature, either IR camera that we have been used a lot, thermocouples and the fluorescence microscopes, temperature-sensitive dyes. So we painting some of this. Those are the sensors that we're trying to work on, especially trying to get the temperature signals at the near surface. So the challenge is really when we reach on the near surface, how we understand the flow field, temperature field, very close to the temperature, very close to the interface side. So we're trying to build up something with the liquid phase using thermocouples, especially small, about 40, below 40 micrometers. Laser-induced fluorescence. Hopefully this can give us some signals in terms of liquid side. Solid side, we're trying to develop in this IR camera, also TSP, temperature sensitive paint. that can give a better resolution than the camera, because the camera is always limited by the space resolution. The best ones, I remember you can go to like a 40 micrometer per pixel, that sort of, or 25 per pixel, that's probably the best limitations. But these dies can give you better space resolution. It's a bit of refraction, and but now this is one of the works we're trying to develop, which is Gerhard will be very interesting to work together. So this is a small bubble. If we want to investigate that, we're trying to understand what's happening very close to the surface, ideally moving into the micro layer space. So we want to get the liquid side, and based on liquid temperature measurement, using NIF and the micro thermocouples, based on the precision is about 10 micrometers. On the surface, we're developing this ISR, which is the thermal paintings, and with the cameras to get the surface temperature, and also below this, this will be our heating wall. The ones here, this is the two new technologies we're trying to develop. We haven't applied this into these sort of boiling situations, but we used in different places, for example, TIR-FM, the total internal reflection fluorescence microscope. In biomedical studies, it's quite established. So this, especially with the temperature sensitive dyes, we can approach the temperature below micrometer sort of range. There's also possibilities of laser interface technology to understand the film, the liquid film thickness there. So we're trying to move towards this way. So these two blue signals are the new ones we're trying to slowly build up. But the bottom line we want to reach on this using TSP and the thermal cameras to reach what's happening close to the surface. So this is set up. So those actually are very similar to the ones that in this morning. And there are some friends show me what happens in TSP in MIT. They also use filming cameras. So we recently got this camera, which is very expensive. So this is supposed to be the best IR camera in the market. The pixel resolution goes to 25 micrometers. Space resolution goes to 4,000 frames per second. So we're using this one to capture the surface temperature. So this is the video can't be played. This is one shot of how this what looks like. We also apply temperature sensitive pens. Those pens they developed in the aerospace engineering. In the past, in aerospace, they want to understand the temperature of this cooling plates, so they just apply some repentance. These pens actually get very sensitive temperatures on the surface. These very cheap methods. So if we can compare this one, this one can be compared with this one, we can establish correlations. In the future, we don't have to use these very expensive, very low response thermal cameras. We can just use these pens to get good signals. So we're trying to relate these two together now. So the manufacturing process is also we're using ITOs as a heater, and then the base is a very transparent diamond base. Another example we want to move into the micro scale is go to interfaces, going to the surface of the evaporating surface. So this is the background as I just mentioned for the solar evaporation. In the solar evaporation, there's people talking about photomolecular effects. They're talking about the enthalpy reductions at the nanoscale. Fundamentally, if we want to solve this problem, heat transfer-wise, we need to understand the temperature at the interface. Very close to the interface. What's the liquid interface temperature? What's the vapor temperature distribution? For example, this is a very, very classical. It's not classical. We're using evaporation equations. We use this equation every time. It's the Schrack equations. They developed in 1953. So using different communication equations, we understand the temperature difference between the vapor side and also saturation temperatures of the liquid. Then you calculate evaporation rate. Normally, we expect the temperature profile, vapor temperature profile, will be something decreasing. So this is that's the case. You start evaporating, the temperature drops in the liquid phase. This is interface. Then the phase is starting decreasing. Then the vapor phase then decrease to the point. So this is our ambient temperature. So you're expecting this is a decreasing process during evaporation. But somehow, if we work out some equations from basic, get rid of these assumptions of Schrack equation, you actually come up with different possibilities. Still liquid phase is decreasing. At the interface, the temperature will drop. But then the vapor phase, the temperature actually are going to increase instead of temperature decrease. So this is a classical case, vapor temperature always decreasing. But in some situations, the temperature may increase. So that means that this lower temperature, ambient temperature is supply heat to the evaporation. So then there are different cases, and then we see the temperature profile at very close to the interface. They may have different profiles than we expected. So this actually will help us to understand how this photomolecular effects or just photo-induced heat transfer evaporation process a lot. So we're trying to perform one of those experiments, trying to understand the temperature of the interface. One is the liquid temperature, another one is temperature just above the liquid. What's the temperature profiles, the temperature distributions within this transition layer? This transition layer normally is Lutsen layer. This Lutsen layer normally is 50 micrometers or so. People always ignore this Lutsen layer. They find just the temperature decreasing from the surface outside the Lutsen layer and then goes to environmental temperature. But there may be something different happens within this Lutsen layer. We're trying to work out establish temperature profiles here. We're also working from some materials perspective, trying to understand this very higher heat transfer evaporation process. We developed some new concept based on hydrogel, which is self-adaptive hydrogel. So this hydrogel has a lot of water inside. When it starts evaporating, it's very quickly evaporating, providing cooling. In the meantime, it actually can absorb the moisture from the surroundings. So it keeps the sustained evaporation all the time. So this is from materials perspective. When you develop these materials with very water hydrophilic, absorbing a lot of water from the surroundings while then dissipating during the cooling process. So this actually will utilize the environmental saturations and the humidities and to supply the heating on the surface. So this is another relating to materials. We use vaccine to increase the thermoconductivity, lithium bromide to increase the hydrophenicities. Now let's move down to a bit smaller scale and something when you can't see it. Then this is what's in the nano scale. This is I have to say, it's very challenging. Micro scale is challenging enough, but if you say nano, sub-micrometer scale is rare. That's where you see. Doing experiments is very rare. Well, there's a lot of challenges. The challenges lies into, for example, and whether you're using optical methods or using different localized sensors, you really can't. Very difficult to reach on the space and the temporal resolutions of that sort of scale. So we try to answer a few questions, even just for this paper. Can we observe the nucleation stage? As we said, the nucleation is the plaquenil stage for alien phase change is happening. But how do we understand? Is this nucleation under solar radiation? Is there really classical nucleation theory, or they are completely different? So we're trying to experimentally investigate nucleation dynamics. And we observe this, the first phase change, how this bubble is produced. Under different heating conditions, heat flux, you may say this is a conduction mode, where people in the past very much interested in the interfacial resistance. And this is conduction mode. You may have the phase changing mode, and the very lower heating power, quasi-equilibrium, bubble growth, collapse growth comes. You may reach a very rapid case, which is everything is highly non-equilibrium. This bubbles phases that goes into a couple hundred meters per second to produce shock waves. So when it collapses, it also produces shock waves. So this is a very strong dynamics of nanoscale phase change interaction with external laser field. So we try to understand this. We also want to quantify visual effects. how this process is interacting with the surroundings, what's the consequences in terms of pressure signal and temperature signals. Now, this is a lot of things moving to physics side. There's a phase change will really focus on this photothermal effects. This is a thermal heating effect. Because in the laser physics, reactions are ultra fast. They have a non-thermal heating, non-thermal evaporating process. Because you just don't have to go through energy, doesn't have to transfer to the photon side. From the photon to electron, and everything study electron dynamics. So they can also have a lot of exchange. So that's a completely different gains. So we are focused on the heating effects. Now we do an investigation. What are the possible experiment techniques that can help us with the dynamic light scattering, spectrums, images, acoustic waves? Then we compile different technologies together, trying to understand which limitations of which technology. Some may give us better space resolution, some may not. Now this is a conclusion. If we really want to go to the nanoscale, reach on nanometer, nanosecond resolution, no single techniques can work. Okay? What we need to do is a compilation of different techniques. If we want to understand this phenomena, there are a suite of different tools we have to combine together. We need to use optical tools, especially like a femtosecond laser and a picosecond laser, those ways. They actually can provide a very good temporal resolution because the pulse can be picked up by a classical pump and probe approach. You can pick up a picosecond or nanosecond, that's no problem. But it's only limited on the higher temporal resolution. What about space resolution? If you want to localize one event is there, so we probably require some localized space resolution, local sensors, fluorescence dyes, and then like TIR, FM. Those are the ways trying to understand the small space within improve the space resolution by nanosensors. Nanosensor for space resolution improvement, optic for temporal resolution improvement. Then together with multiscale modeling, especially when it goes into this ultra-fast regime, everything goes a little bit towards the physics. The temperature itself can't be described the temperature of the photons. You have to describe what the electron temperature, what the photon temperature. So a classical picture here is called a two-temperature model. So this is TTM is a two-temperature model. How we combine this with molecular simulations and then coupled with conventional CFDs. So these are a few possible optical methods where we have been identified and trying to work on. The first one is classical pump and approach approach. The second one is excited stage observation. The third one is time resolved normal spectrum. Of course, the best tools we can use, especially to identify nuclear stage. On the nucleation stage is a SAX, small angle X-ray refractions or small angle neutral refractions. All this requires to use centralized facilities. Normally, we need to apply a certain period of time to do the work here. So this is our final goal, to go to SAX and the science in order to understand this sort of progression stage. Now this is a microscale techniques. What we're really trying to move into is this sort of nanoscale, which we have combined with optical sensors, different pump and probe approach, then plus different nanosensors. And all this combined together, they may not happen in the same events, may not happen at the same time, but we could extract the different information together with the simulations to build up a picture of what's going to happen. So I haven't worked on femtosecond pump probe in the past, but fortunately in TUM, we are very encouraging interdisciplinary collaborations. I talk with these physics guys, they have ultra-fast lasers. We're developing two projects together with the two PhD work on different directions, trying to understand this approach. So we're trying to work out how this is going to happen. Hopefully I can report it to you next time, but we don't have solid results yet. Experiment is one way, but we have to understand the experiment is very limited by resource and also by different operations. Can we develop something modeling approach for this? So this is a different modeling skills from really molecular levels to continuity levels. So people talk about modeling multi-scale, they talk a lot, but sometimes it's very difficult to apply the challenges into different scale couplings. You have a different scale. If you talk about molecular scales, is a nanosecond, nanometer scale. That could be fitting on the nucleation stage. But if you talk about bubbles, everything is millimeters and millisecond levels. So to arrive this coupling is the best, is difficult. Coupling have different ways. You have lookup tables, you have domain decompositions, you have heterogeneous couplings. So we're trying to work on different coupling stages to bring things together. We are very much interested in molecular simulations. How molecular simulations at the nanosecond, nanometer scales, we can use this information to fit into the big pictures of what happens there. So we're developing many works in simulations and different frameworks. For example, we are very interested in understanding this process like electron and photon interactions. Electron and photon interactions by using different two temperature models at the molecular levels, how energy is converting and forming increased temperature, how this information passes into the bubble dynamic process. We have applied this multi-scale to do a bit works. For example, this is simple nanoparticle works was heated by different lasers. If you remember, I gave you a threshold of laser powers, order of magnitudes of laser powers for nanobubbles to be induced. From simulation, we can identify different thresholds of how we're producing single nanoparticles, single nanoparticle, two nanoparticles, a range of different nanoparticles that intensify together, forming agglomerations. Then they have different thresholds of generating different nanobubbles. So this is another example of simulation and how a single droplets evaporation, which looks like here, at a very small scale, at the molecular scale, what happens at the tripoli region. This tripoli region is like similar to this micro layer evaporation at the very close to the surface, the singularity point. So that's also is a lot of mysterious in terms of what happens in this tripoli region, and because clearly continuity equation can't be works on that. So we developed some coupling approaches based on molecular simulations, understand the sleepers, for example, the sleeping velocity, sleeping temperature, the interface, and then coupling this into different the microscopic equations. Now we put all this together to understand this lower pressure evaporation process. This is for the metals. For the evaporation is not only for liquid, it's not only for water. And this example of metal, how metal is starting evaporating. This is a piece of liquid metals, and how these metals are affecting on this process. This is a process which is there's actually they can produce a few videos. So this is a 3D printing process. We need to bring some of these small models into here, trying to understand these sort of keyhole productions, some of the holes that we product during the laser process. This is another example of how we works on different icing, and this is a nucleation simulation. This is based on molecular simulations, how this nucleation happens. But this nucleation is forming the solid nucleus. To initiate the icing process is the other way to the bubble process. So this we actually identify there's a different mechanisms in terms of transfer between this thermal energy, this kinetic energy, and potential energy. We somehow found this is like a heat engine mechanism. So we published recently about this sort of nucleation in terms of heat engine mechanisms at the very fundamental scales. With this sort of information generated and put into big scale studies, understanding, we drop this study shooting, study icing, whether this can help us improve in different situations. This is another example, so we're trying to improve this with LBM. That's Boltzmann equation to understanding a small bubble producing process. So this is based on improve the pseudo methods and also the phase field equipment methods. So we develop all this code by ourselves. So hopefully, and I hope I can give you a brief introduction about what is phase change. I don't think I have any conclusions or summaries to make at these other remarks. I think this is universal, very important, simple, but difficult to understand. There are many applications. If you really want to understand these things, when you understand the multiphysics and the multi-scale nature, especially the lifetime of the phase change, from nucleation to different phase change, and especially in extreme conditions. So we are working on different aspects of this phase change. We don't have a clear answers for many of those. I hope that we can have more ideas later on that I can report. So that should be my talk, my end of talk. Thank you.
Thank you for a nice presentation. A lot of things being done. Now let's open for some questions. Okay, thank you for a presentation. A lot of things being done. And now it's open for some questions, a few questions.
Hi, thank you very much for the presentation. Being a droplet guy, I was interested on the droplet pancake you showed for almost empty space, so no, it was a huge vacuum you had inside. I was just curious for this formation. Normally you can have this, especially heated. It was a heated surface? No, it was isothermal, right?
Just 20 degrees, but for 2 kilopascal, it's heated. You can think about
it. Yeah, it becomes heated, right? But this is the case. Then what's the main explanation for this rebound before it recoils? Because you should have some surface tension preceding the droplet before the impact. No?
Okay, so you. Okay, so you are. So this is you can say if you want to analyze the force. So this is we actually prefer the force analysis here.
Okay.
So the driving force is due to the evaporation, which is especially in this lower vacuum, close to vacuum conditions, and the evaporation is very quickly. The evaporation produces this evaporation force. So if you integration this is the vapor force that produces after lifting force. So they have to counter against the two other forces. The first force is the adhesion force. So it's like the one you mentioned, the surface tension. So it's a stick that tends to stick on the surface. You have to lift it up. You have overcome this adhesion force. Another one, you have to overcome the impacting force. When a droplet starts impacting, it's got the kinetic energy to push the droplet up. So whether this actually can happen depends at the interface, especially on this edge place where there's a force. Whether this is a vaporization, Jordan force can against these two the other forces. If it's okay, then it can lift up. This is very interesting because it only happens. It's the first one. You're reporting this droplet starting bouncing during the spreading process. That's why during the spreading, then it jumps out. All the other drops bouncing, they drops because the bouncing is because of during the recoiling process. The reorganization of surface tension and it goes into this one. During the recoiling process, starting jumping out. So that's why we say this is recorded. So the highest, 85% compared to normal case, the contact time reduction. So when we report this, we're proud that this has been identified. This actually has a lot of applications towards lower vacuum conditions, especially on the coatings. So we are working with some aerospace side, in either the thermal coating, thermal barrier coatings, or ion beam, EB, electron beam coatings. And actually everything happens in the near vacuum situations. The evaporating something, then at the lower pressure, the partly coating something there. I think this could be related.
Thank you.
Thank you very much for the lecture. It's not my research field, but I was really interested about the nanosensors, nano-optical sensors. At that size, quantum effects start to appear? Or?
They do. If you see the color change, all these color changes are quantum effects. They have a decay. They always it always works like an excited stage. You got something incoming exciting to an excited stage, then it decays back. So this decay actually gives you different signals that you can possibly change. Also, this temperature sensitive or different dyes that are changing, the changing colors is because of the quantum effects that are changing colors.
I see. Amazing. That part was really nice. Thank you.
Thank you.
Very nice work. I'm curious about your nucleated body artery pump. You showed
Which
nucleated body artery pump. You have
artillery pump. Okay. Okay. This one. Yeah.
have is vapor going outside from liquid coming
from the side
from top.
Yeah.
Liquid coming from top.
Yeah.
If the liquid come at the position of the vapor and the vapor going out in the center, would not improve the heat transfer.
At the beginning, if you study everything is affected by water. Yeah? Then you study bubbles that are produced. For bubble, if a bubble produces on the surface, so the easy way it goes towards the lower pressure side. It will give a lot of hassles to going from the porous media. So it's the only way bubble, the easy way is from this artery channels that go sideways. So this going sideways, then leave the space, the pressure drops. It's actually helping all the fluids from the up to sink inside by porous force. So this way we have this sort of efficient liquid vapor separation.
If you have vertical arteries, not horizontal.
Vertical can. If you vertical channels, water will be by gravity, it will be much easier to falling down.
Because you have a counter flow.
We actually tried different designs. So this is only two examples. This is one of the artery channels. All these pattern with different size, different height, different diameters, and so the best way is still we found out is the ones the bubbles always coming from the big channels. They're always coming from the sideways. So the question, the limitation factor is how you quickly supply the liquid to replace this the bubbles going. So you need this clearly is the best design, and because the liquid can by capillary force can go from bottom and sides, they can quickly refill all the space with bubble left.
One last question.
Thanks for your presentation, Professor. So I have a question related to the thermal painting. I'd like to know the spatial and time resolution we can achieve with this technique, and how do these resolutions compare with the infrared thermography technique?
They have a similar they have a similar space resolution compared to the best thermal cameras. Thermal camera you mentioned today, for the ones MIT are used is like 100 micrometers per pixel. But this one we're using now is 25 micrometers per pixel. But thermal painting, they normally give you, if you do this well, those are dye sensitive paintings. You can easily reach on 10 to 50 micrometers of space resolution. The good side is tempered resolution because it responds much quickly than thermal camera. Thermal camera, this one we got is the best, they said. It's a 4,000 frames per second, which you're talking about 0.25 millisecond resolution. But this paintings easily goes to below micrometer seconds. They used in this aero engines, when blades was starting turning very fast, a couple of 1,000 RPMs, using these paintings to see the temperature distribution in aerospace side. So we actually, they don't have anyone probably have some in boiling research, but it's very limited, and we're trying to borrow these paintings, and if this can be done, we have the ways of developing this, how we do these paintings, which is using spin coat. We can make sure that we deposit in this one there. Then this actually, you can put on different heating surfaces. That will give you much quicker, also much reliable signals compared to thermal camera. So we also have this thermal camera. What we're trying to do is trying to compare these, establish correlations. Hopefully, this can be used later on. So that's I think these have space resolutions compared to best thermal cameras. Potentially, they have a much higher temporal resolutions.
And we think it's possible to deposit this thermal painting in the heated surface, I mean in the interface between the fluid and the solid.
That's what we deposit now. Yeah.
I try to not have to buy a hair camera. Okay, let's applause Professor Wen again.
Thank you.
Tomorrow, Professor Wen will be around, and if someone wants to
Yeah.
ask him something,
Maybe.
just come out to like that.
I will sit in the office. Gerhard arrange a place for me, and happy to talk with you guys. Yeah?